We are starting with an overview. Week 5 to 6, ROC curves, AUC, and confusion matrix analysis. Welcome! This week, we dive into classification model evaluation using the telecom customer churn dataset. You will explore ROC curves, AUC, and confusion matrices, core tools for checking how well models perform. These concepts help businesses decide when to trust a model's predictions and spot errors early. Ready? Let us get started. Running the cell now. Before running models, let us load our dataset. Let us load the telecom customer churn dataset. We will preview its contents. We start by explaining the data setup for the telecom customer churn dataset. We suppress warnings to keep output clean. We import the pandas library for data manipulation. Import NumPy as NP. We set the random seed to 42 for reproducibility. We specify the URL where the dataset is hosted. We read the dataset from the URL into a pandas data frame. We print the shape, rows and columns of the data frame to understand its size. We print the first 3 rows to get a quick look at the data contents. Running the cell now. This output shows the telecom customer churn dataset loaded successfully with 7,043 rows and 21 columns, providing a rich set of customer attributes from demographics to service details. Notice the mixed data types including categorical columns like e-gender and e-contract and numerical ones like monthly charges. This initial data exploration sets the stage for building and evaluating classification models to predict churn, aligning with our week's focus on using model evaluation metrics. Practice: what are 2 columns you see in the preview above? Here is why cleaning data is important. Step 1: Data cleaning and preprocessing. Real-world data often has missing or strange values. Before any evaluation, let us clean the data for better results. Running the cell now. Now, let us handle missing values and prepare for modeling. Let us check for missing values first. We are checking every column for missing values. We show the top 5 columns with the most missing values found. Running the cell now. This output shows the count of missing values in the top 5 columns of the dataset, revealing that there are none. This confirms our data is complete for these key features, allowing us to proceed confidently without needing to fill in or drop missing data. It's a crucial first step to ensure the quality of our subsequent analysis and model training. Practice: why is it a problem if a column has many missing values? Now, let us remove any rows that have missing values. We will see how much data remains. This comment explains that we are removing rows with any missing values. We remove all rows from DF that contain any missing values. We print the shape of the data frame to see how many rows and columns remain. Running the cell now. After removing rows with missing values, the dataset now contains 7,043 rows and 21 columns. This step is crucial for ensuring that subsequent analyses work with complete, reliable data, reducing errors caused by missing entries. Notice how the dataset size has decreased, reflecting the cleaning intent to improve data quality. Tip: sometimes, you might want to fill missing data instead of dropping it. We need to make sure number columns use the numeric data type. We convert the total charges column to numbers. If it cannot convert, it will become a missing value. We drop any rows where total charges could not be converted. We check the data type to confirm it is now numeric. Running the cell now. Here, the code converts the total charges column to numeric values, coercing any invalid entries, like spaces, to NaN, then drops these rows to clean the data. The output confirms the column's data type is now float 64, which means the column is ready for accurate numerical analysis in later steps. This ensures we have consistent numeric data for reliable modeling and evaluation. This helps us avoid problems in model training. Next, Let us analyze the data visually. Step 2. Exploratory data analysis. Let us understand what churn looks like in this dataset. Visualization helps spot patterns early. Running the cell now. Let us count how many customers left or stayed. We will see how many customers have churned versus stayed. We import the matplotlib library to create plots and visualize data. We add a comment to indicate that we are plotting the churn distribution. We count the occurrences of each churn category and create a bar plot with specified colors. We set the title of the plot to describe what is being shown. We label the y-axis to indicate it represents the number of customers. We display the generated plot. Running the cell now. This bar chart shows the distribution of customers who churned versus those who stayed. Notice the relative heights of the bars indicate whether churn is a common outcome in the dataset. This quick visual helps us grasp the imbalance in the target variable, which is crucial for guiding our modeling approach. Practice: which is the bigger group, churned or not churned? Now let us prepare to train a simple model. Step 3. Classification model setup. We now build a simple classifier to predict churn. We will use logistic regression, a popular starting point. Running the cell now. Let us select features and process categorical variables. Let us pick some important numeric columns as features. We will split data for training and testing. We import the function to split our data into training and testing sets. We specify which columns to use as features and prepare to encode categorical variables if needed. We list the feature columns we will use from the data frame. We create the feature matrix X by selecting these columns from the data frame. We convert the target column churn into numeric values, 1 for the yes and 0 for the no. We split the features and target into training and testing sets, with 25% reserved for testing. We print the shape of the training feature set to see how many samples and features we have. We print the average value of y_train, showing the proportion of customers who churned in training. Running the cell now. The output shows our training set has 5,274 samples with 4 selected features, confirming the data split size and feature structure for model input. The target mean of approximately 0.27 indicates about 27% of training customers have churned, highlighting class imbalance to consider when training the logistic regression model. This setup ensures our classifier learns from a representative but imbalanced dataset, a realistic churn prediction scenario. You will revisit feature choice later in your learning. Let us fit the logistic regression model. We will get probability scores for each customer. We import the logistic regression class from scikit-learn. This line is a comment explaining the next step, training the model. We create a logistic regression classifier with specific parameters. We train the classifier using the training data features and labels. This line is a comment explaining the next step, making predictions. We predict the probability of the positive class for each test sample. Running the cell now. This step involves training a logistic regression model to predict customer churn, but since there is no direct output, the key takeaway is that the model is now ready to generate probability predictions. Notice that we use predict_proba to get the likelihood of churn for each test instance. This sets us up for evaluating model performance in the next step. The focus here is on properly fitting the classifier and preparing it to make meaningful predictions. Those probabilities will be used to draw ROC curves. Let us look at confusion matrices next. Step 4. Confusion matrix analysis. A confusion matrix shows model successes and mistakes. It counts true positives, false positives, true negatives, and false negatives. Running the cell now. Let us see our confusion matrix using test data. We now turn probabilities into predictions with a cutoff of 50%. Then we create a confusion matrix and summary report. We import functions to compute the confusion matrix and classification report. We use 50% as the decision boundary. We create predictions by thresholding the probabilities at 0.5. We compute the confusion matrix comparing true and predicted labels. We print the confusion matrix to see prediction counts. We print a classification report that includes accuracy, precision, recall, and F1 score. Running the cell now. The confusion matrix shows the model correctly predicted 1172 non-churners, true negatives, and 204 churners, true positives, but also made 128 false positives and 254 false negatives. Notice the imbalance in recall, 0.90 for non-churn but only 0.45 for churn, highlighting the model's struggle to identify churners consistently. This output connects to the lesson by illustrating how the confusion matrix breaks down prediction results to diagnose where the model succeeds and where it needs improvement. Practice: do you see more false positives or false negatives? Next, we dive into what the ROC curve and AUC mean. Step 5: ROC curve and AUC. The ROC curve shows the trade-off between true and false positive rates. AUC stands for area under the curve. It measures overall performance. Higher AUC values are better. Running the cell now. Let us plot the ROC curve and calculate the AUC. We will visualize model performance with an ROC curve. Import functions to compute ROC curve and AUC score from Churn. Comment indicating calculation of ROC curve points next. Calculate false positive rate, true positive rate, and thresholds from test labels and predicted probabilities. Comment indicating calculation of AUC next. Compute the area under the curve, AUC, score using test labels and predicted probabilities. Comment indicating plotting of ROC curve next. Plot the ROC curve with AUC score shown in the label. Plot a dashed diagonal line representing random guessing performance. Label the x-axis as false positive rate. Label the y-axis as true positive rate. Set the plot title to ROC curve. Display the legend explaining plot lines. Show the plot on the screen. Print the AUC score to summarize model performance. Running the cell now. The ROC curve plot visualizes the balance between true positive rate and false positive rate at various thresholds, illustrating the model's ability to distinguish classes. The AUC score of approximately 0.80 indicates good overall performance, meaning the model correctly ranks positive instances higher than negatives about 80% of the time. This aligns with the lesson's goal to evaluate classifier quality beyond simple accuracy metrics. How does your model's AUC compare to guessing, which is 0.5? Thresholds let you decide what counts as a positive prediction. Step 6: Varying thresholds and model sensitivity. Changing the probability threshold changes errors. Let us see what happens if we lower the threshold. Running the cell now. Notice how confusion matrix results change. We will predict positives more often by lowering the threshold to 30%. Let us check the new confusion matrix. This line explains the effect of lowering the threshold on predictions. Here we create predictions by labeling probabilities as 1 if they are at least 0.3. This line computes the confusion matrix comparing true labels and predictions. We print the confusion matrix to see the classification performance with the lower threshold. Running the cell now. Lowering the threshold to 0.3 increases the model's sensitivity, as shown by more positives predicted. Notice the higher false positives, 328, compared to before, and more true positives, 316, detected. This confusion matrix highlights the trade-off: lowering the threshold catches more positives but also raises false alarms. Practice: why might a company want fewer false negatives for churn? Let us interact. You get to pick a threshold. This is a prompt asking you to input a threshold to test. You input a threshold value between 0 and 1 here. Predictions are made using the threshold you provided. We calculate the confusion matrix for these predictions. We print a message showing the threshold used. We print the confusion matrix to show the results. Running the cell now. Here, with a threshold of 0.65, notice the confusion matrix shows 1264 true negatives and 87 true positives, but also 371 false negatives and 36 false positives. Lowering the threshold from the default typically increases true positives but may also raise false positives or negatives, illustrating the trade-off in sensitivity. This output helps us understand how adjusting the threshold directly impacts the model's error types and overall sensitivity. Try several numbers. Notice what changes each time. If you find this helpful, please consider subscribing for more practice tutorials. Let us summarize what we learned. Step 7. Recap and best practices. Always check for missing data before training. Look at ROC curves and confusion matrices, not just overall accuracy. Experiment with different thresholds based on business needs. Use AUC to compare classifiers fairly. Running the cell now. Great job! You practiced important analysis skills today. Now let us challenge ourselves by trying a model with just one feature. This is a comment indicating a challenge to try using a new feature. We select O monthly charges as the new feature to use. We import standard scalar to standardize the feature values. We create a scalar object to perform standardization. We apply the scalar to the monthly charges column to scale it. We initialize a logistic regression model with a fixed random state. We train the logistic regression model using the scaled feature and target values. We get the predicted probabilities for the positive class from the model. We calculate the AUC score to evaluate the model's performance. We print the AUC score rounded to 2 decimal places with a descriptive message. Running the cell now. The output shows an AUC of 0.62 when using only this monthly charges feature to predict the target, indicating moderate predictive power from this single feature. Notice this approach isolates one variable to evaluate its individual contribution, reinforcing the lesson's emphasis on carefully selecting and understanding features before training. This step highlights best practice, assessing model performance beyond accuracy by using metrics like AUC and ensuring meaningful input data. Practice: which model had a better AUC score, full or one feature? Here is an extra task for you. Extra challenge. Try varying your feature selection or test out tree-based methods like decision tree classifier. How do your confusion matrix and AUC results change? Running the cell now. Share your discoveries in the video comments. Let us wrap up. End of lesson recap. You learned how to clean and prepare data, split data for modeling, interpret confusion matrices, plot and understand ROC curves, use AUC as a summary metric. Keep experimenting and practicing. Running the cell now. Ready for more? Try this lesson with another dataset next. Thank you for joining this lesson. If this was helpful, please subscribe and comment below with your favorite lesson moment. See you in the next video. Running the cell now. You are building great data mining skills. Keep going.